Good morning, good afternoon, everybody. We're just going to give attendees just a few minutes to join Tech Talk here before Dave graces us with all of his knowledge.
All right, you can hear me fine. You can see the Tech Talk banner on the screen?
We can,
well?
yes. All is well. Audio is clear. So yes, Dave,
good,
the group is yours.
Good. All right. Should we wait? Are we waiting still just a minute or two? Or have we got our registered attendees here?
I think you are good to go, Dave.
Okay, very good. All right. Welcome, everyone. Welcome to this month's Tech Talk. In keeping with our RF basics here, I want to take and today talk about quality of service. It's a pretty broad topic, and I'm going to simplify it to the point where it's going to be just so simply explained. I hope that we're all going to understand why some of these radio systems have some of the controls in them that they do. So let's get going here. We're going to take a look at quality of service from 3 different points of view. All of them are going to end up representing the happy customer. So we're going to look at RF channel activity. We're going to look at from the point of view of service levels, and we're going to look at from the point of view of service types and what we can do with our system. All right. So typical internet traffic. This is again, I warn you, this is very, very simplified. But typical internet traffic is a series of requests and responses. There is over time, people, subscribers to your network will take and click their mouse and generate a request for information to some point out on the internet, and that some point on the internet might answer, or it might forward it on to somewhere else that answers, or who knows what happens. But ultimately, from the subscriber point of view and from the access network point of view, there is a request and a response, and every response has been triggered by a request, by and large. If a response comes from the internet all by itself, it's generally called bad activity by the firewall, and it is rejected. So generally speaking, in a network, there has to be a response. Then if there's a request, if there's a request, then the response comes back from the internet server, and there we have it. Now, if everything were that straightforward and easy on the network, no problem. It's not. What we have is a case of in real channel activity. When we have requests, the response doesn't necessarily come right after the request. It can come sometime in the future. So here we have a request from the blue subscriber. There's some other activity on the network here, and the response finally comes back, much later in time than the request was made. And so this is really, really typical of activity. There can be a number of different things that happen to us here. One is that the request and response time can be short, it can be long, it can be multiple frames, multiple PDUs, it can come in multiple intervals. Websites are, oftentimes you'll notice that a website starts to download, it'll download its frames and whatever else it has, then it's busy crunching the data inside of it, and then finally it downloads the rest. And so we have all of this activity that is completely asynchronous, meaning that there is no timing for it. It happens when it happens. You don't schedule a mouse click. You don't schedule the beginning of an internet conversation. You sit down at your chair and you open up your browser and you look at your browser and you say, oh, I want to go here. Maybe you type in your URL, or maybe you click on a favorite, or whatever it is that you do. There's no schedule for that. It happens when it happens. And so the response comes back from the internet when it happens, when the response is ready for your request. And so we need to keep this in mind as we're explaining how these broadband wireless QoS mechanisms very basically work. The size can be any size. It can be very small, as little as 32 or 64 bytes, or it can be very large. It can be jumbo frames. It can be up to the response could be up to 9,000 bytes in size, and so the frame may be split up into smaller units or not, and it's just so unpredictable. And the one thing that we can be certain of in our world, anyways, in the broadband wireless world, it's a time division duplex medium by and large, meaning that there's a time for transmit, there's a time for receive, there's a time for uplink, and there's a time for downlink, and all of these never happen at the same time. The transceiver is either in transmit mode or receive mode, but it's never in both at the same time. So traffic activity is never in parallel. It would be great if it was, and there's some huge advantages to in efficiency to having things happen in parallel. The cellular network, for example, is frequency division duplex, and frequency division duplex often has, always has things happening in parallel. There's always transmission going on at the same time as receiving. So we don't have that luxury in the spectrum that we've been given as broadband wireless operators. We are definitely time division duplex. We have uplink, and then we have downlink. The other thing that's different all the time is that our link quality varies from one to the other, and so all of the frames, even though in this cutesy pie little drawing that I made, that the frames look like they're all equal in size. The uplink same size, downlink same size. That's not the case. In the real world, I may have a case. Let me drag my whiteboard down here just for a second. All right. In the real world, I might have a case where I have a link that's operating at QAM 256, very high quality link, and the frames on that link are all very small. The requests may be very small, and then right beside it I have a link that might be operating in QAM 16, let's say, and so the requests are a little bit longer, and the responses are a lot longer for the same volume of data. So the lower that we go in modulation level, the longer that we're occupying our medium in order to take and pass that traffic. This is all completely common sense so far. Absolutely. So it goes to reason that we've been talking about link budget for the last 3 months here. And so our goal is to make sure that we have the link quality that we need to be able to support the data rates that we're going to supply to our subscribers. So if we're going to have a high data rate service, then they're going to need a high modulation level that supports that data rate that we want to sell them. If we're going for a type of network that we simply allow everybody to connect and they give them a relatively low data rate, then we can go down in modulation levels, and we can allow the network to reach much farther, but the data rate that we're connecting at for those far subscribers is going to be much lower. So we're going to take up more time, therefore we have less overall capacity on the network compared to the capacity-based network where we've built it for speed. All right, drag this out of the way. Okay, so some of the characteristics of the traffic, very interesting. Asynchronous traffic has interframe spaces or interframe gaps between the frames. This interframe space allows the TDD network to do other things while we're waiting in between the request and response from the user to the internet and back again. So the reason that we have the capacities that we do is because the access system is very efficient at filling in the gaps with other tasks that it needs to do. So subscriber one, if we let me just go back here. So if subscriber one has a request, if we waited for the response back and then the internet to say I'm finished, then we would have wasted all the time from here to here. So this would have been wasted time. In this particular case, we have a request. We have a request here. We have a response over here, and this time that is in between the request and the response has been filled in with another conversation. So some other subscriber unit has talked during that interval. And the same, this goes on the network all the time. The larger the interframe spacing, the more conversations that we can have at one time. So you can imagine this. If this were, let me take away my little scribbles here. If we were running, if this network, let's say subscriber number one here, the blue subscriber here, has a relatively poor link, and subscriber green has a relatively good link. So if subscriber one and subscriber two here, where the poor link and the good link, we're looking at the same website. For example, they're looking at the same website. If subscriber, the subscriber two with the good link, we're operating at QOM 64. Well, let's say QOM. Let's go all the way. Let's say QOM 256. It's got a very good link, and QOM and subscriber one is talking at QOM 16. Just for a second. So he for the same data, this is going to take 64 times longer. So this is times 64 longer data units over the air than what this QOM 256 is. So you can see that by this time that the air can get pretty used up as you know, we have poor quality links mixed in with good quality links. Good quality links, the time value that they're spend on the air transferring their data very short. The poor quality links take up the majority then of the time that that this base station has to deal with its subscribers. So let's go ahead here. All right, so we end up with this metric called utilization. Utilization is the ratio of the time spent passing data traffic divided by the total time the medium's available. So if I'm spending 1 millisecond passing traffic in the downlink and I have 2 milliseconds of time available in the downlink, that is 50%. That is the definition for 50%. If I have 1 millisecond of traffic and I have a 1 millisecond available to me, that traffic in that 1 millisecond is making the link 100% utilized. That's the way this math works. Not too difficult. And depending on what the system is, it might be pretty easy to calculate. Normally, the calculation is converted into data rate. And so if I have a sector that has a demand on it of 70 megabits, and the sector itself is capable of 100 megabits, then that's considered to be 70% utilized. That from a time perspective, that may be correct. But if my link quality is if I have more links that are poor quality than good quality, then that my time on the link might actually be much more. My data rate might reflect the fact that the link itself might be very close to 100% utilized, because the time passing the traffic divided by the total time the medium's available might be almost full up. So I got some little characteristics here that picked up over the years. At 50% utilization, the medium appears fast. And I say appears because nobody's actually measuring it. You're measuring it by the time you click your mouse, between the time you click your mouse and the time you start to get a response back from the internet. And if that time is really short, then the network seems fast to you. And responses arrive very shortly after the subscriber clicks the mouse or presses enter. At 80%, the network starts to seem a little sluggish. The medium seems a little sluggish. Responses can be both quick or may take some time, kind of all in the same time. So we've all witnessed that before, where traffic to a particular website is congested. There's a medium along the way that's nearing 100% utilization, and so we click on our mouse and one time, and we get the response very quickly. 30 seconds later, we go to turn the page or whatever it is after we've finished reading the page, and it takes forever for the second page to load. And we think that there's something wrong with our computer. That's a typical consumer response, but there's not. It's a case of the medium being less available than it was before, and the utilization is, of course, much higher. As we near 95 or 100%, the medium starts to get very slow. And oftentimes what happens when we hit this number is that the subscriber often makes multiple mouse clicks. So you click the, I do it all the time. I go to a web page and I click on, let's say, a link on the web page. Nothing happens. What do? You click it again. You wonder, did my mouse actually work? And you click it again. Well, what this does is it generates multiple requests of the same information. And so what we end up doing by doing that, of course, is congesting the link even more, because now the first click was actually heard by the network, and the network's trying to respond to it, but it can't. Then it gets the second, third, fourth click, and so it's like quadrupling the activity on the network, and it's all because of the fact that the medium is actually highly utilized and is very slow. And when we do hit 100%, the medium is actually broken. What that means is that the link is active enough that I cannot start a new data conversation on that link. So let's say we've got a typical access point. We have maybe 50 or 60 subscriber units on that access point. And we have maybe 30 or 40% or 50% activity of the SMs are active on that link, and our demand is equaling the network capacity. So our medium is nearing 100% utilization. What happens here is that if a new subscriber comes along to initiate a conversation, let's say I want to check my email. Let's say I'm not on and I want to check my email. So I open up my Outlook or my Thunderbird or whatever it is, and it goes to get the email and nothing happens. So oftentimes, I've witnessed it many times as I'm troubleshooting networks, where there's a stream that's running. Maybe one of the people in the home is watching a Netflix movie, for example. Netflix and Prime and all of these services, they'll probe when you first start a movie. They'll probe your network and they'll see how much capacity you actually have, and then they'll try to take it all. They'll try to take as much capacity as you'll give them in order to have the best movie viewing experience that you can. And that's great as long as all you want to do is just watch the movie, but that may not be the case. And if we have enough people on our network doing this, then we can approach this 100% utilization value. And at that point, then I can't start a new conversation. And so anybody who wants to come on the network with something new, of course, they are shut out. They will not be able to join the network. And so we have a terrible situation here where our subscribers are getting less and less happy by the second. And it's really common in rural internet today. It's actually quite common to run into this issue. but there are some solutions. And so we're going to talk about what happens here in some of these solutions. All right. One of the other characteristics of a broadband link is that as our utilization gets higher, generally speaking, our latency goes higher as well. If we have a situation where the increasing network load equals longer latency, the sector is going to seem like or the medium is going to seem like it's unpredictable. And so you get to quite quickly, you get to the point where your subscribers on the network are going to know when to sit at their computer and when they won't sit at their computer, because they're going to run into this unpredictability. So we need to take and as much as possible, eliminate the variables that we have when we're providing a particular internet service. So that's the goal here, is to slightly increase the latency on traffic during low utilization periods. So what we actually want to do from the point of a solution here is, in this case, we want to take and slow the network down just a little wee bit, and in order so that we can take and remove that funnel or remove that choke on the network as the utilization comes up. That way there isn't going to be that huge difference in between unloaded network and loaded network. And so we want to take and do this. The point we want to do this, of course, is it could be taken to an extreme, and you know, a system could add a lot more latency than it needs to, and then remove that latency as the network is busier and busier, and then the network will feel exactly the same whether it's unloaded or loaded. But you don't want that. You want the network to perform well when it's able to perform well, and you want to be able to take and control it in those periods of time when the utilization starts to become very, very high. Second thing, we want to take and make sure that our latency either reduces or stays the same. In most cases, we want to maintain the latency that we have as utilization increases. So we don't want to have a curve. We do not want to have a curve where I've got a latency. So here is utilization, and this is latency, and I don't want to have that. What I really want to have, let me try to erase this. What I really want is I want something like this to happen, so that as my utilization comes up, my latency will flatten out, and it will be more or less the same as over. I didn't draw that very well. It should be flat, but it should be. We want to get to the point when we have a higher utilization that our latency is actually flattens out and doesn't change very much with the utilization as we load up our network. This is the goal. This is one of the goals. And of course, the bottom line is that traffic with transit time restraints, we want it to arrive on time. So in the case of VoIP, for example, I will probably have a requirement that I need to pass my VoIP frames every, say, 20 to 30 milliseconds or something like that, or maybe a little bit more than that. I need to make sure that at the very upper limit of this time that I will be able to get my voice traffic through there. So I need to ensure that this particularly time-sensitive traffic gets across the network on time. If it doesn't, I end up hearing the robot voice, and of course nobody wants to hear that. We've all heard it, and nobody wants to hear that. We hear it oftentimes on our Wi-Fi at home when we're on a conference call. Let's say we're on a video conference call, and all of a sudden the other end starts to say, "Oh, you're sounding like a robot," or your voice is all choppy, or whatever. That is because the traffic that has this transit time restraint, the video frame needs to arrive and the audio frames need to arrive at the other end on time and in order so that they can be reconstructed correctly. And so you have a good representation of what's, looking into the camera and talking into the microphone at the originating end of that traffic. So there we have it. We have those three very basic issues. All right. So what's the issue? What's the real issue here? We have a utilization thief that runs amok on our networks all the time. It comes in two main forms. There's a number of other that I could list down, but I'm going to speak about it from an RF perspective right now. Is that we have really 2 points that make that steal our utilization, drive it up unreasonably. The first one is poor link quality. All modern systems use rate adaptation, which means that the modulation level or the modulation scheme or the modulation itself changes depending on the link quality. We call it modulation scheme because there's forward error correction that's built into every level of modulation on every broadband device. Always some of the data that's used that transfers from the sending end to the receiving end. Some of it is used to do error correction, and so they can mathematically correct sometimes errors in the that are generated over the RF link and recover that data at the receiving end. When we get to the point, though, that we can't recover the data anymore, when there's too many errors, then we switch modulation levels and we come down. And what happens when we come down in modulation level is that we now increase the amount of time that it takes to transfer the same amount of data. So if we're at QAM 64 and we have to go down to QAM 16, we are going to take and 4 times, we're going to occupy the link 4 times more than we were before at QAM 64. So we have kind of a conundrum here. We lower the modulation level to reduce the signal to noise ratio that we need to recover the data, but at the same time we do that, we're forcing ourselves to use the medium longer in order to pass that traffic. And so poor link quality is a utilization thief. The next one is our buddy retransmissions. Retransmissions, when the forward error correction fails, almost all broadband systems will take and report that failure from the subscriber unit back to the access point. Says, I didn't get that. Can you say it again? That's called a retransmission. Can you say it again? And so oftentimes on a retransmission, it will be retransmitted at a lower modulation level than what it was originally transmitted at. Sometimes not. Sometimes some manufacturers retransmit the first one at the same rate. And if that one fails, then they reduce the rate in order to try to guarantee the success of the frame. But at any rate, the retransmission, first of all, even if it's at the same rate, takes up twice as much time as what the original traffic did, right? Because I'm retransmitting the original traffic. So I've already taken then and doubled the amount of time that my this one particular subscriber unit is listening on the air. Secondly, many manufactured systems will send the transmission at the original rate. Let's say it's QAM 256, but there's a fade going on, and I no longer have my 28 or 30 or 32 dB that it takes to support that QAM 256 of signal to noise ratio. So let's say it drops down to 25 or something like that. Well, now I'm firmly in QAM 64 territory. So lots of systems will retransmit at the same rate once, and then retransmit the second time at a lower rate. So if it's a long fade, or you know, the anomaly is out there for some considerable length of time, the modulation level will reduce. We'll take up more time on our link, of course, to transmit the same data, because it's the same data. The data has to go from in this case, the access point to the subscriber module. It's already destined to go there, and the subscriber module has the smarts in it to hold the data up until it's all complete, until the Ethernet frame is correct, and then it sends it out the Ethernet jack to the device that's connected to that subscriber module. So, in saying all that, we have this multi-rate algorithm that will take, and yes, it will save us from losing the data, which is, of course, very, very important. But all multi-rate algorithms, I don't know of any that are not, all multi-rate algorithms reduce the modulation level very quickly, in order to be as error-free as possible. Then they recover very slowly, and generally, it's a function of the traffic that are passing across the link. So let's say we had a link, with a fade, a very deep fade. Let's see, very deep fade, but it's actually quite short in time. So in this deep fade, I'm passing traffic, and my QAM 256 traffic suddenly starts failing, and maybe I retransmit that frame, and the fade is still long enough that it's still there, so I fail that retransmission, and then the access point will then take and lower the modulation level to QAM 64, and it will resend the frame again, taking up more time, but the rate is lower. The bits per second rate is lower over the air, and we end up in the situation where maybe it's successful at QAM 64. The radio will stay at QAM 64 for some time, expecting the errors to come back if it cleared, and they won't go back up again. So if we have this multi-rate algorithm reduce the modulation level, it takes, usually quite a volume of traffic in order to have that modulation level recover. It does not come back up as fast as it goes down ever. So those are our utilization thieves. All right, so let's start talking about the solution. We've spent 30 minutes talking about the problem. Let's spend the same amount of time on the solution. All right. So from a link quality perspective, we have to implement a good design. We need to reduce self-interference as much as possible. That's the number one point right there. So we build the network properly. We do a good configuration. We make sure our channel plan is fine. If there's other addressing that we need to do, such as colors, or to maintain sector, to maintain CPE on their own sectors, or if we have to do PCIs and LTE, whatever the case happens to be, we need to do a good design. And the other point that is actually quite important in all of this is that our spectrum, our RF spectrum is one of the constraints that we always have as we're building a broadband network. So this good design needs to use only as much RF spectrum as you need. You can't, it doesn't make any sense to do a reuse zero, if you like, on every sector on a different channel, a different frequency, because at that point in time, you're actually wasting that RF spectrum. There's no need for it these days. We have GPS synchronization. We have other features in the broadband equipment that we can take and reuse spectrum much quicker than every sector being on its own frequency. We need to maintain a clean RF environment. In other words, this is now, we have to take and enable our channel plan. So yes, we have to avoid self-interference, but the second thing is that we have to avoid external interference also. In these days, all the bands that we're using have some, commonly using anyways, have some sort of shared spectrum activity. And so be it 3650 or you know, whatever in Canada here, what that's going to become in the future. In the US, the CBRS is shared spectrum. 5 gigahertz is the other very common spectrum. It's definitely shared. For anybody who's operating in 900 megahertz in ISM band and 900, that is most definitely a shared spectrum with lots of people operating in the band. And so we have to take and design our network so that we avoid this external interference. Thirdly, we need to make sure that we install our CPE at ranges that support the link quality that we need. So if I've determined on my network that QAM 64 is absolutely the minimum level that I want to install a CPE at, then I have to maintain that installer discipline, that installation discipline to make sure that I continue to work at what a subscriber needs in order to get them above that particular threshold. So not only in the past, when radio systems were all line of sight and we had zero non-line of sight capability, there were lots of times that you'd get 30 or 40 requests for service in a particular sector, and you had to turn down 50% of them or more because they just didn't have a link to get there. So the point here is that nowadays with the OFDM protocol such that it is, and the over-the-air protocols that we're using, we do now have the ability to have the CPE behind a tree or two, or a row of trees, or whatever the case happens to be, and we still might be able to make our required link quality with the CPE even at that. But we might need to do a little bit more work. We might need to make sure that the CPE is up high enough, or we might need to make sure that the CPE is on the right spot on the house, there's a lot of skill required when you're installing this equipment. Not only is the skill required at the in the network operations center to be able to configure all of this equipment correctly, but at the installer's perspective, it is an art to be able to install a CPE on a house. Look at the link. You're up on the roof. You analyze where it should go, what it should do, and install it that way and have it work perfectly every time. There are my hats are off to installers that have a very high success ratio, and there's lots of them that do now. Every day I'm fortunate enough to be able to peruse through some networks when people have questions that require a little bit of support, and I see some networks that are just fabulous in their performance, and so my hat's off to that, because that is a case of maintaining that installation discipline in order to keep the quality up. So from a data perspective now, this is from a link quality perspective. From a data perspective, I got some controls in the network that I need to be able to use. Almost everybody today has a maximum information rate controller of some sort. I need to take and be able to set those correctly. If I set those wrong, then I am going to be burdening the network with tasks that maybe it can't do. So I need to take and understand how these MIR controls actually work. I need to commit some bandwidth to, if I have time-sensitive protocols like SIP running on my network for VoIP, I need to be able to commit some time to it, but I need to take and intelligently commit the time so that I am not overly committing time to this. If I need 80 kilobits per second of time, there's no point in me setting that committed information rate to 1 megabit because I'm going to be wasting 900 kilobits of that in order to take and the definition of committed information rate in as far as broadband wireless is concerned, that bandwidth that you commit is in fact set aside for as long as that CPE is connected to the access point. So let's say we have a situation where I've got 20 SIP customers, and I'm using G711, and so I need 80 kilobits in each direction for each conversation. And I have some people that have 2 lines. So therefore, I need to have some at 80 kilobits uplink and downlink, and I need to have some at 160 kilobits uplink and downlink. And so if I have enough of these on the sector, it's going to add up to an appreciable amount of data. So let's say I've got one phone in every residence, and I'm going to commit 80 kilobytes, or kilobits per second, I should say, kilobits per second to each one of those conversations, and I have 20 subscribers on this sector, then I am committing 20 times 80 or 1.6 megabits are going to be committed to that service. And as long as those CPE are connected, I am going to reserve that 1.6 megabits so that it's always available. The more I commit, the more that's sitting there doing nothing most of the time, because we know that when we're on the phone, we're only on the phone for some part of the day, most of us anyways, for some very short part of the day, and the rest of the time the medium is sitting idle. And so if we're committing that a large volume of VoIP service to that, then we're going to have lots of idle medium, and it's actually a waste. So finally, the third thing is I need to use higher OSI, that's OSI layer, traffic filtering effectively. So the Open Systems Interconnect is I'll talk about that in a minute here, is the definition of how data devices in our world today talk to each other. All right, some conditions, some things that happen on a typical wireless link. All right, in the network, in the modem, the Ethernet frame is dismantled into a stream of bits. These bits are delivered to a digital analog converter, and that is converted into an RF carrier going out over the air. We know it's OFDM, or there's a number of different types of RF carriers to create different signals, but nevertheless, these principles, these 3 functions are what occurs in the modulator. Over the air, all modern broadband equipment test the channel conditions. They probe, they sound, there's all kinds of different terms for it, but nevertheless, they're testing the conditions, and they're seeing what they can do. They oftentimes will advertise to their subscriber units. The access points will advertise their capabilities, and oftentimes when the subscriber module joins the network, it advertises its capabilities to the network. So the network knows how to speak to a particular subscriber unit. The quality of the RF signal determines the size of the messages that can be grouped together, and so the higher the quality, the larger the group typically, or the shorter the time that we take handling the traffic that's on demand at any particular moment. Typical minimum signal quality, we've been over this a bunch of times, but the modern broadband equipment runs typically from QPSK up to 256 QAM. And these numbers vary slightly by manufacturer, and everybody normally puts the numbers on their data sheets in some form or another. You can figure out what this is, but that's what I need to be able to take and be able to plan my network, be able to get the right capacity out of my network. When I leave the modem, when I have passed over the air and I'm decoding and been decoding, the demodulator converts the RF symbols back into a bit stream. Data integrity is tested with forward error correction, or sometimes other integrity mechanisms as well, such as scrambling, for example, is a method of testing the medium. Any errors are mathematically corrected if possible. If correction is not possible, a message is sent back to the transmitter to send the data again. And the same thing happens at the transmitter. If it received a bad frame from the connected router or switch, then it would ask for that frame to be retransmitted. And we're no different over the air. If we have errors that cannot be corrected mathematically, we have a retransmission. And almost all systems today ACK good data and NAC bad data. There's very few systems today that operate on what used to be called no news is good news, and we have ACKs and NACs running back and forth. NAC when it's when the frame has failed, and ACK when it's good. So on a typical wireless link, we have a number of different interface speeds. We have different situations happening. In this link that I've got here, this typical link here, I've got a gigabit Ethernet connection between my network router and my access point itself. My RF link, though, it's using a 20 megahertz channel, and so it's the multi-rate algorithm supports QPSK to QAM 256, which generally means then on that channel I've got about 150 megabits of capacity, give or take. So here I have 1G, here I have 150. If I have a full stream coming in at 1G, I cannot pass that whole 1G of traffic over the air, because I can only deal with maybe 150, maybe 130, or maybe it's 200, or whatever the number is, depending on the equipment manufacturer. I have a limit as to how much data can go over the air, and it's always less than what the interface that's connected to it is in modern equipment. So in the days of having a fast Ethernet interface here, when that was the king of the hill, well, it was possible then to have more RF capacity on a typical link than it was on the backhaul link, but those days are pretty much gone. So various interfaces have different data rate capacities. Data buffers are used to temporarily store data delivered by a fast interface being clocked out by a slower interface. So in the case of the 1 gig here, I have data coming at 1 gigabit per second on this minus the interframe spacing time. And since I can't clock it out over the air, I can't talk to the subscriber units that fast. I'm going to store it. I'm going to temporarily store it right in here. And then I'm going to keep clocking out data out to the subscribers at the rate that I can do it. And we're going to play a statistical game where the actual demand on this is going to be low enough that I can take and transmit all of the data out of this buffer here, or keep the buffer, at least room in the buffer, so that any new incoming traffic has a place to go. This is the action on a typical link. So it's not always that data demand equals available capacity. Sometimes demand can be higher than capacity. So here on this network on the left-hand side here, if we take a look at these boxes and add up these boxes, if I assume that I've got 100 megabit capacity at the AP, I can add this up and I'm going to find I'm less than 100 megabits. And so in this case, I'm golden. There's no issues whatsoever. Over here in the right-hand side case, Now, I've got some issues with this network because I've got one subscriber unit that's got a monstrous demand right here, and a couple other subscriber units that the demand is pretty healthy. And what it ends up doing is ends up shutting out. I have no availability then for these other two subscriber units because these three are taking up the entire capacity of the access point. I run into trouble. So if my capacity is limited by link quality, then it takes fewer CPE to saturate this sector. And so I need to, all the things we've talked about so far, I need to be very diligent at making sure that everything's okay. So we have a solution. Almost everybody now today in manufacturers deploy some sort of leaky bucket algorithm, and it's just exactly that. And so I thought, well, let's use a leaky bucket as the graphic example of what goes on. You can imagine if this is the gig E connection up here. Let's go gig E. Oops. The gig E, and this is the radio connection out here. I have mutual capacity into the top of my bucket. I have a big open space here, right? Big open space. And then I have simply smaller holes in the bottom of the bucket so that I can leak I can leak my data out at a controlled rate that I'm not going to swamp my RF link here. I'm going to maintain a data rate that I can support over the air. So what happens here is that as data pours into the bucket will eventually fill up, and then hopefully the demand will momentarily reduce, and the bucket will then it can take and lower the level. So as my demand is lower, my leak in the bucket is able to take and keep the bucket relatively empty. What happens when my little bucket here gets full? So let's so when I have the case where my demand is huge, and so I've got a big volume of traffic that's coming into my bucket, and of course I've got my controlled rate coming out of my bucket. When the bucket gets full, when my bucket is now up to the top, what happens here is that my leaky bucket will tell the device that it's connected to it that, hey, I am going to toss a frame. So a frame goes out the door and gets thrown away. It reports this drop, and at the layer 2 on the Ethernet interface, the frame is then retransmitted. But some time has gone by here to reduce the demand momentarily. Let me get this back to the full size. There we go. And so the demand is reduced momentarily. And so then the bucket has a chance to get some more space in it. This is how the maximum information rate algorithms in almost every bit of broadband equipment, every manufacturer of broadband equipment out there works in some way. They'll call it tokens. There'll be different ways of exploiting this, of actually making the MIR operation work. But essentially, this is what's going on: is I have a pail, a buffer. I have a buffer that's collecting this traffic and is clocking out of the buffer at a particular rate. So my goal is to keep room in the buffer. And as long as I have room in the buffer, I can start a new conversation. I can do all kinds of things here for my network. My network is healthy if my bucket is not full. My network is congested if my bucket is full. But if my bucket's empty, of course, it's empty, and all the traffic that comes in immediately leaves, and away it goes. But in this case, what I've done now is I have this room here that I can take, and when the demand is increased, my subscribers don't feel it. When my demand decreases, my subscribers feel exactly the same. That's the point. All right. Where's the bucket located? The bucket is, of course, located just before the RF deck. So when there's congestion over the air, when something happens here, it gets reported to the bucket. The bucket then will take and maybe reduce this rate because there's RF congestion out here, whatever the case happens to be. And if the demand is low enough, the bucket still won't fill up, and we'll be happy. If it reduces too much, then of course our bucket fills up right away, and then we're throwing frames away. And if you look at the counters for almost every piece of broadband gear these days, there is a discards, and you'll see the discard frame number trickling. And it's trickling because it is taking, and the leaky bucket is telling the device connected to it that, oh, I'm full. And it happens, maybe once every couple seconds or whatever it happens to be, and away it goes. So we're going to end up here with a full meal deal. What would be the ideal system? So I got a graphic here of the OSI model down in the bottom left-hand corner here, and the definitions for the various layers in here. Leaky bucket A. No, let's talk at the start at leaky bucket B. Leaky bucket B is the one we're talking about inside the radio system. Leaky bucket B controls the traffic on the physical layer and the data link layer here, OSI layers 1 and 2. So layers 1 and 2 are controlled right here. So as the medium is able to deliver this traffic across from the access points to the subscriber modules, and of course back again, this leaky bucket controls that activity. In leaky bucket B, I recommend that everybody have. As a matter of fact, I had a conversation this morning with one of our customers this morning about the configuration of leaky bucket leaky bucket A, which happens to be in their case, it happens to be from Preseam. And so leaky bucket A is used to control layers 5, 6, and 7. So the session layer, the presentation, and the application layer are controlled by leaky bucket. So if Netflix wants to probe the network and try to use up all the capacity that it's given, leaky bucket A will intercept that, and it will say, oh no, you've only got 5 megabits or 7 megabits or whatever it is, even though I know this is a 35 megabit stream that are capable over here. I'm going to limit streaming here to 7 megs or something like that. So every video stream that starts in here gets 7 megs of capacity or some number like that. That would be the case here. That way, the leaky bucket A looks after the streaming from Netflix or Prime or Apple or whoever it's from, and then leaky bucket B then looks after the medium. So the leaky bucket B then controls the physical interface and monitors that. Leaky bucket A monitors essentially the software. You notice here that transport and the layer 3 here, the IP layer, the network layer, are not covered in this model because they have their own retransmission mechanism. TCP/IP has its own retransmission mechanism, and we don't want that to fire. We want to have our layer 1 and 2 and our layer 5, 6, and 7 operate well enough that we never have an IP retransmission. That's the goal. That's the goal on how to make this thing work properly. So that's more and more as we get into higher and higher data rates. The demand now is 5010 as a minimum, and soon it's going to be 120. I have in my house here, I have 175 megabits of capacity on a GPON network, and so all of these mechanisms are absolutely necessary as we're going along here. So that is the essence of radio quality of service. I hope this was informative and a little bit insightful. So definitely one of my passions to talk about this and to implement and to make it work. Want to thank you for your time, And if you got any feedback or comments, suggestions, whatever you want to say, just send it to marketing@mbsiwave.com, and between Nicole and I will answer any questions that come in. If you have new topic suggestions, I'd be wonderful to hear them. And so want to thank you for your time today, and have a good rest of the day.
Thank you so much, Dave. And the next Tech Talk is going to be after the holidays on January 20th. So we look forward to that one.
All right, everybody, have a good day, and we'll talk to you soon.
Thanks, everybody.